Good morning, everyone. Welcome to Guru Brahma classes for JEE and NEET. Today we are discussing about adiabatic process. Adiabatic process from the chapter thermodynamics, right? So adiabatic process in which exchange of heat between system and surrounding does not take place. That means here let us take the system. So the system is not taking heat. It is unable to absorb heat. It is unable to release heat. Here Q is equal to 0, Q is equal to 0. That means this system is insulated. What is this? Insulated. Insulation means this is made of adiabatic wall. Adiabatic wall. So what is adiabatic wall or adiabatic boundary? If the system is not allowing the heat, that means it is insulated. Insulated means its boundary is adiabatic in nature. Adiabatic means which does not allow heat to flow through it. That is called as a adiabatic. So now here Q is equal to 0. That means it is not taking heat, it is not releasing heat. So from the first law of thermodynamics, we can say that we have one formula, and what is that formula? Delta U is equal to Q plus W. Okay. Here Q is equal to 0. When Q is equal to 0, then delta U becomes W, or minus delta U becomes minus W. Right? So we are speaking about work done in adiabatic reversible process. So we are deriving a formula to calculate the work done. Now delta U, that is change in internal energy, is equal to work done, right? And already we know that delta U is equal to N CV delta T. NCV delta T. Here you can find CVM. M means molar. So what is CVM? If it is written M, then what is that CVM? Molar heat capacity. Molar heat capacity at constant volume. What is that? Molar heat capacity at constant volume. If we come across through CPM, M is just represented that it is calculated for 1 mole, molar. So molar heat capacity at constant pressure. Okay. So here N is number of moles, CV is molar heat capacity at constant volume, and delta T is change in the temperature, right? So as delta U is equal to W, I can write W is equal to NCV delta T. NCV delta T, right? So instead of CV, I can write, for example, let us see. We have a relation Cp minus Cv is equal to R, which is called as Mayer's equation. Molar heat capacity at constant pressure minus molar heat capacity at constant volume is given by universal gas constant, R. Okay. And there is a ratio, Poisson's ratio, Cp by Cv is equal to gamma. Cp by Cv is equal to gamma. It is Poisson's ratio. So these two things we need to remember. We'll come across through how to derive Cp minus Cv is equal to R. So Cp minus Cv is equal to R, where Cp is molar heat capacity at constant pressure, Cv is molar heat capacity at constant volume. So what is this called as? This is gamma. The ratio of heat capacities at constant pressure to heat capacity at constant volume is given by gamma, right? So from this what I can write, Cp can be written as Cp is equal to gamma into Cv. So let it be equation 1. Let it be equation 2. Substitute equation 2. Substitute equation 2 in 1. Then what do you get? Cp is equal to gamma into Cv, no? So gamma into Cv minus Cv is equal to R. So let us take Cv common. Gamma minus 1 is equal to R. Instead of Cv, I can write Cv is equal to R by gamma minus 1. Understood? So Cv, what did we get? Cv is equal to R by gamma minus 1. So let it be equation 3. Substitute equation 3 in this work done formula. So let us write work done is equal to N. So instead of Cv, I can write it as R by gamma minus 1 into delta T. Already we know that T final minus T initial. Final is taken as T2 and initial is taken as T1. Okay. I can write it as W is equal to nRT2 multiplying minus nRT1 by gamma minus 1. Okay. So if during compression or expansion we will have initial temperature, and if final temperature is also given, then we can use this formula. So this formula is used when final temperature during that adiabatic process is given. But if final temperature is not known, see, if final temperature is not known, as the gas, in this gas we are taking ideal gas, right? Let us consider in the system we have taken what? Ideal gas. In the case of this, for ideal gas, we know ideal gas equation PV is equal to nRT. Okay, PV is equal to nRT. Now P2 V2 substitute is equal to nRT2. See here the number of moles are not changing, so I am taking only N. The temperature is changing, and P1 V1 can be written as nRT1. Now let us substitute this P2 V2 and P1 V1 in this equation. In the equation number, let us take it as equation number 4. On substituting, what do we get? W is equal to P2 V2 minus P1 V1 by gamma minus 1. So these two formulas can be used to calculate work done for adiabatic reversible process. Hope so you understood. Next, coming to let us see. This is again adiabatic. We are speaking about adiabatic process. In this adiabatic process, we know that Q is equal to 0, right? And delta U is equal to, right, W according to first law of thermodynamics. Right? If T2 is less than T1, the work is done by the system. This shows that adiabatic expansion leads to cooling. So work done formula, normally we have seen that W is equal to R by gamma minus 1 T2 minus T1. Okay. So if T2 is less than T1, then work done will be what? Negative. Right? If T2 is less than T1, if T1 is greater than T2, then smaller minus larger quantity gives you negative. What does negative work represent? Negative work represents that work is done by the system, expansion work. Okay. So final temperature is less than initial temperature. That means when work is done by the system, then it leads to decrease in the temperature. That decrease in the temperature leads to cooling. Decrease in temperature leads to cooling. So this condition we need to remember. Next, the same one, if you see, work done is equal to R by gamma minus 1 into T2 minus T1. If T2 is greater than T1, the condition here, let us see this condition. T2 is greater than T1. T2 is greater than T1, then work done will be positive. Positive work means work is done on the system. If work is done on the system, work is equal to positive. So we are getting positive work. T2 is greater than T1 represents that final temperature is more than initial temperature. That means the system gets heated up. So adiabatic compression leads to heating. Adiabatic expansion leads to cooling. Understood? Okay. Next, coming to work done in irreversible adiabatic expansion. Irreversible process already we have seen. Let us consider an irreversible process. An irreversible process occurring in one step. So this is some gas enclosed in a cylinder. Okay. So here there are two. We are speaking about two conditions. One is free expansion and another is intermediate expansion. So free expansion, what is meant by free expansion? Free expansion means, first of all, we have to remember that expansion of gas into vacuum where external pressure is equal to 0. What is that? Expansion of gas into vacuum. That means there is no external pressure, but gas is expanded. For example, let us take here. This is a large container. It is separated into two compartments. There is gas here. There is vacuum. Here is vacuum. Vacuum represents that there is nothing here. Nothing. No air, no gas, nothing is here. Now when you keep a hole, for example, let us take a hole. Here we are keeping a hole, small hole. Then what happens? This gas expands, spreads. So what is the work done by the gas now? Work done, we know the formula, minus P external into dV. P external is 0. So 0 into delta V. that is equal to 0. So work done is 0. Whether it is isothermal process or whether it is adiabatic process, whatever the process it is, when gas is expanded into vacuum, which is called as a free expansion. In the case of free expansion, always work done is equal to 0. Work done by the gas is equal to 0. Okay. So that is in intermediate expansion. We are speaking about intermediate expansion. Suppose the pressure is suddenly released to 1 atmosphere and the gas expands adiabatically against this constant pressure. So there is some constant pressure, some P external is there. Against this constant external pressure, what is happening? The volume is changing from V1 to V2. So let the volume be V1. After expansion, let the volume be V2. Okay, against a constant and external pressure. Then work done is given by, already we know that work done is given by minus P external into V final minus V initial. Okay. But if, for example, in the question, volumes are not given. So this was once asked in competitive examination JEE main. What is that? Volumes are not given. So P external is given and P1 and P2 are given. And we know that considering this gas as ideal gas, what can be applied? Ideal gas equation can be applied. PV is equal to nRT. Okay, so then V is equal to nRT by P. So instead of V, let us apply this nRT by P. Then work done will be equal to minus P external. V2 means N number of moles taken in this cylinder is constant. We are not adding gas, we are not releasing gas. So then what you take, N is constant, R is constant, temperature is changing and pressure is also changing. So nR T1 by P1. Then minus P external into nR, let us take common, then T2 by P2 minus T1 by P1, right? And that is equal to minus nR P external into P1 into P2 T2 P1 minus P1 P2. So this formula, this can be used for irreversible process. Work done in irreversible adiabatic expansion. So this formula can be used. When this is used, when initial volumes and final volumes are not given and initial pressure and final pressures are given and this expansion is happening against a constant external pressure again. And initial temperature and final temperatures are given. Then we can go with the formula and solve it. Okay, right? Next, let us see here. We are speaking about now graph comparing isothermal process and adiabatic process. So let us see isothermal first of all. Isothermal process means T initial is equal to T final, right? Delta T is equal to 0. Okay, delta T is equal to 0. So when temperature is constant, from Boyle's law we have studied that PV is equal to constant. If PV is equal to constant, change in PV will be equal to 0. PV is constant now, change in PV will be equal to 0. D means change, small change, infinite change. Then dPV is equal to P into dV plus V into dP is equal to 0. P into dV is equal to minus V into dP. dP by dV is equal to minus P by V. So what is dP by dV? dP by dV here, let us take a graph. When you draw a graph between P and V, already it is seen here, isothermal process P and V. What graph you are getting? You are getting a graph like this. The slope of this graph, so slope is dP by dV. Negative slope. See, so what is this? Negative slope. If you want to find if you want to find the slope, we have to draw a tangent. Okay, so this tangent where it is intersecting on y-axis, and that is theta. Tan theta is slope. Okay, is that a tan theta is the slope. So slope is negative. Slope is negative. See, this negative represents that the slope is negative. That's it. When you come to adiabatic process, for adiabatic process, PV gamma is equal to constant. PV gamma is equal to constant. We will derive it now in this session. PV gamma. Okay. Then if PV gamma is equal to constant, change in PV gamma will be equal to 0. Then dP by dV, what we get? Minus gamma, okay, P by V. Right? So what you are getting? You are getting slope. So slope adiabatic by slope isothermal. Then what do you get? Slope adiabatic is minus gamma P by V by minus P by V. Then slope adiabatic by slope isothermal will be equal to gamma. Slope adiabatic is gamma times to the top slope isothermal. Right? Slope isothermal. S represents here slope, right? So gamma, if you take gamma, Cp by Cv is called as gamma. Before we have discussed this Poisson's ratio. Gamma is always less than 2 and greater than 1. Greater than 1 and less than 2. Gamma for monoatomic gases is 1.66. Gamma for diatomic gas is 1.4. Gamma for triatomic gases is 1.33. So always it is greater than 1. So when it is greater than 1, automatically slope adiabatic will be greater than slope isothermal. So adiabatic process slope is greater than isothermal slope. That is the reason why. So let us come to this graph. In this graph, if you see, which is having more slope. See, this graph will have more slope. This is having more slope than this graph. So for example, A to B, let us take. A to B graph is having less slope than A to C. So A to C graph is having more slope. So when you compare these two, A to B is which graph, which process graph, and A to C is which process graph. A to B, when you compare these two, A to B will be having, as it is having less slope, it is isothermal process. So isothermal expansion. It is adiabatic expansion because initial volume is less and final volumes are more. Okay. So coming to the work done. So how can you recognize isothermal and adiabatic when two graphs are given? The one which is having more slope will be adiabatic and the one which is having less slope will be isothermal. Right? So coming to work done, PV. So the area under the PV graph will be the work done. So this is isothermal. What will be the area of this graph? This will be the area, right? This area. The area under PV graph will be the work done because work done is equal to what? Minus P external into delta V, right? Delta V product. So this area comes under this product. So the area under PV graph will be the work done. So let us take for adiabatic process PV. So this is adiabatic process, right? So compare these two, which is having more area. Area under isothermal process is greater than area under adiabatic process. So work done isothermal process will be greater than work done in adiabatic process. So that is what here you are seeing. Work done in isothermal process will be greater than work done in adiabatic process. Okay. If you compare those graphs, then if you compare those areas, then you will be able to, here the area under this graph is more, area under this graph is less. That's it. Next, coming to final temperature in isothermal process. See, isothermal process, this is isothermal process. And this is, let us take adiabatic. What is that? Adiabatic process. What is this process? Isothermal process. Right? We are speaking about expansion here. Speaking about expansion. Expansion work is done by the system. Work is negative. Here this wall in isothermal process, here the wall is diathermic wall. Diathermic wall means which can allow the heat to flow through it. Heat can enter into the system, heat can leave the system. So work is done by the gas now. We are speaking about expansion work. During expansion, what happens? Work will be done by the system. Right? Now, when work is done by the system, there is possibility, as this boundary is diathermic boundary, heat can enter. Q is positive. Heat can enter. When heat enters, then there will be less change in the temperature. There is no change in the temperature. Initial temperature can be equal to final temperature. But when coming to adiabatic process, The situation is not like that. Why? In adiabatic process, this wall is insulated. Q is equal to 0. It cannot take heat, it cannot release heat. If it is doing work, then delta U will be equal to W. Minus delta U will be equal to minus W. That means if work is done by the system, that's called as a expansion. Work is done by the system. What happens automatically for doing that work? This system, where did it get the energy? Where did it get the energy? It has got energy, or it has absorbed energy from the gas. So it derived energy from the gas and it has done the work. Okay. When the energy of the gas decreases, automatically the temperature of the gas decreases. So here the temperature, final temperature is less. Here, as the boundary is diathermic boundary, when it is doing work, it absorbs heat energy from the surroundings, and by using that heat energy, it is doing work. So here the temperature, initial temperature is equal to final temperature. There is chance, possibility, but here as heat is not absorbed, whatever the work it is doing in adiabatic process, whatever the work it is doing, for doing that work, it has absorbed energy from the gas. So temperature is decreasing. That means here final temperature in isothermal process will be greater than final temperature in adiabatic process. In adiabatic process, when the gas is expanding, the energy of the gas decreases. When the kinetic energy of the gas decreases, automatically its temperature decreases, because kinetic energy is directly proportional to average kinetic energy is directly proportional to its absolute temperature. Average kinetic energy is directly proportional to its absolute temperature. Right? Next. So reversible expansion, reversible process, adiabatic, we are speaking about the adiabatic reversible process. Adiabatic process, already we know that Q is equal to 0. Q is equal to 0. So here dE or du, whatever it is. So internal energy can be represented as E or U. So du is equal to dW. A small change in internal energy is equal to small change in work. And we know that du is equal to NCV. CV means molar heat capacity into dt. dt is small change in temperature. And we know that dW is equal to minus P external into dV. A small change in work due to small change in volume. These two are equal. Okay, these two are equal, and during reversible process, this is reversible process, we can say that P external is almost equal to P internal, or pressure of the gas. Pressure of the gas. Okay. And considering that the gas taken here is ideal gas, ideal gas. So pressure exerted by the gas is equal to PV is equal to nRT by V. Right? nRT by V. So instead of external gas, if I use pressure exerted by the gas, then what do we get? NCV dt is equal to minus. So external pressure is taken as internal pressure. Internal pressure is nothing but pressure exerted by gas. Pressure exerted by inert gas is equal to nRT by V. So nRT by V into dV. N and cancel. Let us move temperature left side. Then what do you get? Cv into dt by T is equal to R minus R into dV by V. So both sides we have differentiation, we can integrate it. On integration, then what you get? Integrating Cv into dt by T is equal to integration of minus R dV by V. Okay. What do you get? Cv into integration of dx by x is equal to log x, like integration of dt by t is equal to natural log t, that is equal to minus r, integration of dv by v gives you log v. X log t is equal to log t power x cv is equal to x log y is equal to log y power x, right? We know this formula, x log y is equal to log y power x. Then what do you get? Natural log v power minus r log. That means t power cv is equal to 1 by v power r. V power minus r is equal to 1 by v power r. Then t into cv power v power r is equal to constant. This is constant, right? Then let us see here. Divide with cv. T into cv by cv into v into r by cv is equal to constant. Right? Then what do you get? T into v power r by cv is equal to constant. Already we have seen before that cv is equal to r by gamma minus 1. Then r by cv is equal to gamma minus 1. So instead of r by cv, I can use here t into v power gamma minus 1 is equal to. So the relation between t and v we have derived. What is that? Relation between t and v. In adiabatic process, t into v power gamma minus 1 is equal to constant. T into v power gamma minus 1 is equal to constant. This is gamma, right? Understood? Next, let us see now only we have seen that t into v power gamma minus 1 is equal to constant. This we have derived. Now we are deriving the relation between t and p. Relation between t and p. So use this, and we know that And we know that from ideal gas equation, PV is equal to nRT, right? We are deriving relation between T and P. So instead of V, what we can write? V is equal to nRT by P. So when you take a particular gas, when you consider or take a particular gas, we are experimenting this. We are not adding gas. We are not releasing gas. Then here n is equal to constant. N is equal to constant, and R is also constant. So let us take only T and P. So substitute in this volume. Then what you get? T into T by P. We are not using what? N and R. N and R are constant. So gamma minus 1 is equal to constant. Then what do you get? T power 1 into T power gamma minus 1 into P power 1 by P power gamma minus 1. 1 by P power gamma minus 1 gives you P power 1 minus gamma is equal to constant. So then T power 1 plus gamma minus 1 into P power 1 minus gamma is equal to constant. So 1 cancel, then T power gamma P power 1 minus gamma is equal to constant. Divide it, T power gamma by gamma, P power 1 minus gamma by gamma is equal to constant. So gamma by gamma gives you 1. So finally what you are getting? T into P power 1 minus gamma is equal to constant. So you can use this equation, or this equation. Both are same, right? So relation between T and P, T power gamma into P power 1 minus gamma is equal to constant, or T into P power 1 minus gamma by gamma is equal to constant. What is the relation between T and V in adiabatic process? TV gamma minus 1 is TV power gamma minus 1 is equal to constant. So this gamma minus 1 is only for V, not for T. Okay. Then let us derive the relation between P and V. So already we have studied that TV, what is the relation between T and V? TV gamma minus 1 is equal to constant. T into V power gamma minus 1 is equal to. So now we want the relation between P and V. So V should be there instead of T. You know that PV is equal to nRT again. Instead of T, I can write it as PV by nR. N and R are constant. So write P and V. So P into V power gamma minus 1 is equal to constant. Right? So P into V power 1 plus gamma minus 1 is equal to constant. 1 and minus 1 get cancelled. PV gamma is equal to constant. So this is the relation between P and V. PV gamma is equal to constant. So before we have seen, while we are deriving the relation between the slopes, when you are comparing the slopes of isothermal process and adiabatic process, we came across through PV gamma is equal to constant. So PV gamma is equal to constant, T gamma into P power 1 minus gamma is equal to constant, and T into V power gamma minus 1 is equal to constant. Right? Hope so you understood very well. If you don't understand, rewind the video and again play it. So when you are watching a video, you will have flexibility to pause the video, rewind the video, play the video. So how many times you want, you can do it. That is the flexibility of recorded videos. Hope so you understood very well. Thanks for watching the video up to the end of the video. If you like the video, please like, share, subscribe. Thank you very much. Meet you in the next video.